此心此念此悲我心，不痛不苦绝无欢喜。观山观海人生冷暖，听风听雨忘却疏寒。此心此念此悲我心，不痛不苦绝无欢喜。欢喜。海上有明月，云飘荡天际，心无言语靠近，林上上烟花微笑。观山观海人生冷暖，听风听雨忘却疏寒。此心此念此悲我心，不痛不苦绝无欢喜。观山观海人生冷暖，听风听雨忘却疏寒。此心此念此悲我心，不痛不苦绝无欢喜。上有明月，云飘荡天际，心无言语靠近，林上上烟花微笑。上有明月，云飘荡天际，心无言语靠近，林上上烟花微笑。观山观海人生冷暖，听风听雨忘却疏寒。此心此念此悲我
Good morning, everyone. Welcome to the first AAMA Technology Salon in the year 2021. Our topic today is quantum computing. 欢迎大家参加亚杰社会2021年第一场科技沙龙。今天我们的主题是量子计算。量子计算大概6、7年前开始进入大众的视野。3年多前，中国宣布开通全球第一条连接北京、上海的量子通信干线。去年底，中国科技大学发布9张量子计算机原型机，据称比现在最快的超级电脑快几百万倍，甚至几百亿倍。当然，这个是非常震撼。但这个是什么概念呢？什么是量子计算呢？有什么应用呢？离现实有多远呢？中国这方面是否领先呢？今天我们很高兴与我们长期的合作伙伴，香港中文大学深圳创新创意创业中心 CIDE 及我们新的合作伙伴香港科技园创投基金共同举办这一场线上科技沙龙，很荣幸邀请的3位专家给我们讲解分享。Now, quantum computing entered into common day vocabulary about 6 to 7 years ago. 3 years ago, China built the world's first quantum communication channel, linking Beijing and Shanghai. Late last year, the University of Science and Technology of China announced its 9张 quantum computer prototype, which is said to be a few million times or even a few billion times faster than the fastest supercomputers currently available. Of course, this is mind-boggling, but what does it mean? What exactly is quantum computing? And what are the applications? And how close is it to reality? Is China leading in this area? Today, we are delighted to work with our long-term partner, Center of Innovation, Design and Entrepreneurship, CIDE of the Chinese University of Hong Kong, Shenzhen, and our new partner, Hong Kong Science Park Corporate Venture Funds, to bring together 3 experts to enlighten us on this topic. Eric Ho, one of our directors, will be the moderator. Over to you, Eric. 以下时间交给我们的董事何占辉先生主持。
谢谢。大家好，我是何占辉 Eric。今天我们很高兴、很荣幸邀请了3位专家来到解析一下这个量子计算。他们会从不同的维度去讲一下量子计算。首先，我们邀请杨森博士。杨博士是香港中文大学物理系助理教授，他会从这个科学层面去讲一下量子计算。杨教授，请。
谢谢。So let me share the screen. So first, I want to thank the organizer for inviting me here. So I'm going to speak from the point of view of science, that what is quantum computing. So first, let's start with the very simple things. What is a quantum? So you probably have the common life experience that what is a classical, because quantum is always opposite to the classical cases. So as we learn from the high school, from the college, we usually learn about the classical situation. One of the features is most quantity you learn are continuous. So for example, time is continuous, the space is continuous. You can always divide things into infinite small. For example, also the voltage, the power, everything seems continuous. But later people discovered that if you go to small scales, actually everything is quantized. So for example, here people can see each atoms. Also, if you look deeper into the atom, you can see it's made out of some quantized particles, for example, electrons or nucleus. So, and even, for example, the general quantity like the length, the time, the energy, the electricity, everything, if you go down to a small scale, it will be quantized, not continuously. So this brings into a completely new, different world. So, and what is advantage of this world for the information science? One of the feature is now it's become quantized, which is just similar like the idea of the classical information, because as we know right now, you're looking at the computer or cell phones, everything here are based on this classical bit. So that means information are decoded into several bits, and each bit can be either 0 or 1. So it's also a quantized phenomenon. So for quantum world, then we can use this quantum nature again to convey the information. Now, there is a difference between this classical quantum bit than this quantum bit. So in the cloud situation, each bit is either 0 or 1. But in the quantum situation, you could be any so-called superposition of two 0 and 1 together. So this you can see from this schematic. So if you imagine this is just Earth, so the North Pole representing 0 and South Pole representing 1. So the classical bit can just either be North Pole or South Pole. But a quantum bit can represent any state on Earth. So you just have to find out what is a longitude and what is a latitude in this Earth. So then you would ask, okay, so I understand what North Pole and South Pole is 0 or 1. But how about anything in between? So for example, in this state, it is in this weird form, 0 plus 1. So what exactly is this 0 or is this 1? So this comes to a very strange concept in the quantum situation. This is called quantum superposition. You probably heard it in a lot of public talk about Schrödinger's cat. The exact definition is for an unknown quantum state. The state can be simultaneously into several different states. For example, it could be simultaneously either in the cat is alive or cat is dead situation, as long as you don't measure it. So you don't know what exact state it is. So then you would ask, okay, what is a different compare with I have just prepared a dice on a box, but I just close this box and give to this box to you. So you don't know what exactly inside information, but you know, I prepare it. You only open the box, then you find out the result. That's actually quite different from the quantum situation. So we can use this scheme to show that difference. So in the cloud situation, for example, I prepare a number and I put it inside the box. I keep it unknown for you. But in reality, the state is already fixed. It is only one out of all those 2 to the power n combinations. So I already prepare like 110 in the box. So it always will be 110, no matter you open it or you don't open it. But if this is really a quantum bit, I prepare a state like this. Actually, unless you measure the state, otherwise the state can be superposition of all those states. So it could be all the possibility of 2 to the power n situations. So this gives you a much bigger probability. So for example, people say, now here on the screen, you have 300 qubits. And if you make a superposition of all 300 qubits, actually the possibility of state is even more than total number of atoms in this universe. But this is under the conditions that you don't measure it. So now you can see measurement will be also a quite important concept in the quantum world. So quantum measurement is actually not only just a readout, but is an interaction. So again, let's come to this Schrödinger's cat situation. So before we check the status, the cat can be either in the live or dead situation. But when we measure it, it will collapse to one of the possibilities. It's either alive or dead. So this is something, an interaction that this measurement also lead to the result. So this is another important concept which we'll go into deeper when we come to the detail about quantum computing. So quantum is quite a strange system. And in this system, people already start to explore in different directions for this information science. For example, they are in the quantum computing, which is the topic of this whole seminar. It's actually also quite popular right now working on this quantum communication. Supposedly it can bring a much more secure network for the information transmission. And also there are a lot of people working on the sensing part, which you can bring much better sensor compared with traditional sensor in the modern technology. So in this talk, we will mainly focus on quantum computing. So people always ask us, what kind of quantum computer you can make, right? Can you make playing game faster, for example? Can I make the office work much easier? So actually, this is not a general purpose for the quantum computing. So actually, so what is so quantum computing may not be a system that work out every possible jobs actually. So the mainly quantum computing are good at are these two directions. One is this quantum Fourier-based algorithm, which I will explain in detail what it is. Another thing is doing quantum simulation. So quantum computer mainly is supposed to be doing these two jobs and much better than the classical counterpart. So let's first go to the first one. What is a quantum Fourier transformation? We probably know for the classical computer, there are a lot of algorithms based on Fourier transformation. I think this is one of the key algorithms for the classical information science. So what it does is it checks the spectrum of the signal. So actually, quantum is always based on this wave function, and this wave has very similar feature like classical wave. This feature is called interference. So interference, for example, you can see it in the classical counterpart situation. For example, you throw two stones onto a lake. On the surface of the lake, you will see a ripples, and then this two wave will start interference and form some periodic pattern. You can also do this with a string hooked up with the end, and you do a standing wave. You can see the standing wave, and look at for the standing wave, there are millions or even billions of atoms right there, but they behave periodic pattern right on top of it. So this periodic pattern corresponds to this wavelength of this wave. And this information is quite simple, but it's quite useful. So those periodic information is the information quantum computer can derive much faster from this wave pattern. So for example, this is one of the famous algorithms, the Shor's algorithm, supposed to be able to factorize a semi-prime number much faster than a classical computer. How did they make it? So they use actually very simple algebra problem, because you want to factorize a number, you have to divide the number to certain prime numbers. And so what the residue you have is periodic. So this periodic pattern corresponds to a periodicity which corresponds to this prime number. So if you can find out this periodicity faster, you can get this prime number faster. So this is eventually what is behind the Shor algorithm, how eventually it can crack this password of this RSA-based password. By the way, this RSA password system, encryption system, is just a system right now we are using every day for our banking, even for this video conference. So this RSA encryption is based on the semi-prime number factorization. So in this case, if you can really do this factorization with a Shor algorithm faster, you can crack this password easier. But one thing we have to say is it needs a lot of resources. It needs a lot of qubits to do this factorization, right? So this is one thing we want to say. But I think the take-home message is why quantum computer can be powerful in a problem like Shor's algorithm is they can find out the periodicity faster. So this is there are a lot of algorithms behind in this direction. And there's another direction, as we say. So this is called quantum simulation. So what is quantum simulation? So you probably wonder why China, US, Japan are making super big classical computers. They make the supercomputer and they compare every year who is the best. And what are these computers doing right now? More than half of the times they're actually doing simulations of materials. For example, right now we are trying to combat this COVID-19 virus pandemic, and people try to make new medicines. And how do they design new medicine? They cannot just try all the time in the chemical labs, fabricate different molecules. They first have to do screening to see what are the possible candidate molecules they can use. So what they have to do is, for example, they arrange hydrogen, carbon, oxygen, all this molecule into certain formation. Say, this is a new molecule we design. And let's see what is the property of this molecule. So they don't do it directly in the chemical ways. They first simulate by the super big computer to check what is the property supposedly we can get. So the supercomputer eventually is actually simulating a quantum system, because they are simulating, for example, 100 carbon atom, another 200 hydrogen atom, try to form together. They calculate out what is the energy level of those molecules. Now use a classical computer to simulate a quantum computer is very hard, because they are just two different systems. So that's why you cost a lot of resource to simulate those things, and we cannot simulate too much. So I think usually the biggest computer can simulate roughly a few hundreds of atoms. So we only can simulate such a small system because we use a classical computer to do this job. So people think, okay, now can I use a quantum system to simulate a quantum system? So for example, now I want to simulate a molecule with, for example, 1,000 atoms, which is not possible in the classical computer case. I can just find 1,000 atoms. I just have to be able to manipulate those atoms and to design this atom just behave like what I want them to behave. And then I simulate this material, then I check what is the property out of it. So this is about a quantum simulation. So if we can build a quantum computer and we can control each of those atoms, we check what is the property out of it, we can actually make a big breakthrough for example, design new material, design new medicines. So those are another big field of what quantum computer eventually can do. But the quantum computer is not that easy to make. So why is it so hard? I think there's a very famous saying from the great physicists. They say, to make a quantum computer, you want this qubit to interact strongly so you can make all these operations. But you don't, on the other hand, you don't want this qubit to interact with anything else until we want to measure them. Right? So you want them to interact for the gate operation, but you also don't want them to interact if you don't operate on this. So this makes the life very hard. So one thing we will have is the errors. So we will have a lot of error from surrounding. This is similar for the class situation, right? For example, in the classical, if you have a memory in the hard drive, you always wonder if your information can be distorted. For example, the 0 goes to 1, the 1 goes to 0, then I lost my information. This is something always worry for both quantum computer and classical computer. But besides that, quantum computer have more issues, because now instead of just using 0, 1, use the North Pole or South Pole as my information, we use actually every position on this Earth as different information. So now if you only use 0, 1, for example, if you in the North Hemisphere, you say, well, this is North Pole. If you're in the South Hemisphere, you say that's South Pole, right? It's very easy to make the cut. But now if you say, are you in Hong Kong? Are you in Shenzhen? That's probably no different for 0, 1 situation, but it's make a big difference if you think about the quantum phase. So that's why quantum computing or quantum qubit are much more fragile. So it can easily go a little bit. For example, the qubit information is changing from the Hong Kong to Shenzhen, your information get lost already. So this is why I show you here different systems right now people are using for quantum information science. And for each system, they have some limited, we call coherent time. You can see the time you can keep the information for real. So you can see it's quite limited. And so this brings a huge problem. Now you'll say, well, classical computer also have the same issue, but we have this error correction algorithm. So for quantum counterparts, they also have quantum error correction, but it's much harder to make. So, so we already know that even in classical computer situation, right? Even you have the classical error correction, you sometimes also face this situation, right? That means the error cannot be corrected and then your system crash. So, but still, in most cases, in classical computer, you can have the logic classical bit. That means your information gets stored there, stay forever, because you have other qubit to help to correct the errors. For quantum computer, right now, the situation is kind of heavier. So we actually do not even make the logic qubit yet. Although people are now saying that I have 50, I have 60, I have 100 qubit, that's all physical qubit. So that means they are only staying quantum for, let's say, a second or at most a few hours. After that, it's become classical. The error is too much. So people are still working very hard to make a really effective quantum error correction. For example, people propose that we can use, for example, the surface code to make a better encoding. And people also propose that we can use from topological features to make a topological quantum computer that makes qubit live longer. But now, very strong landmark we still didn't reach yet is to make one logic qubit. This is something we still are trying hard. So this is one of the problems for quantum computing. Another roadblock is making this multi-qubit gate. This is also very common in the classical situation, right? You have this AND gate, OR gate, and much more complicated gates for making the calculation, because you don't want just one qubit, but you want a system of many qubits. In quantum algorithm, you also need to do, for example, many 2-qubit gate or multi-qubit gate. Now, if you think about your qubit layout is as complicated as this, to doing 2-qubit gate over different qubits become much more difficult to scale up. So that's another issue posed for the quantum computing. But with all these problems, people are still making a lot of breakthroughs in the quantum computer. For example, recently, there are so many breakthroughs on making some quantum simulations. Let me show you a few papers and the result. So once, 2 years ago, by Google right? They make this superconducting Johnson junction-based quantum chips, and what they do is they get 53 physical qubit, and they make a simulation. What they simulate? They simulate is a quantum system. Although this quantum system may not be that useful, right? It's actually a pseudo-random quantum chip. They want to just simulate what will be the output of this random quantum circuit. And they compare, of course, with the classical computer. Well, use a classical computer to simulate a quantum computer. It's always difficult and resource demanding. So that's why they say, well, we went against all the supercomputers because we use a quantum system to simulate a quantum system, while they use a classical computer to simulate a quantum system is much less effective. Although, as we said, right, we don't have error correction. So therefore, the total fidelity is only 2 out of 1,000, right? This is very, very small, but people are still trying to improve this part. Another work is the famous work everyone now probably knows. This was done last year in Hefei by Professor Jianwei Pan's group. They also simulated a system. So where they simulated is the so-called boson sampling problem. So eventually, it's just thinking about a lot of identical photons going through some beam splitter. This is like the quantum version of the Gordon board. So they try to simulate this system and to measure what is the probability of the distribution of the bosons. Of course, we know this kind of problem is very hard for the classical computer to calculate out. So doing quantum simulation directly, you can measure the probability instead of calculating out. Right? So this is another advantage under certain problems. The third example I want to show you, it was done just a few weeks ago in Harvard. What they did is they actually tried to simulate a solid state materials. How did they do? You know, solids are made of periodic patterned atom. Now they arrange a big array of atoms. So they get a 256 atom, they put into a periodic array. They can control those atoms. They can manipulate what the interaction strings between each atom. Therefore, they can simulate a solid from all this atom cloud. So they use this atom system to simulate a solid. So in this case, they could potentially to design new materials with this quantum simulator. Right? So those are the 3 examples. I think it's really going forward at very fast speed. So eventually, people can maybe use this system to simulate a real material, simulate real medicines for the good purpose. Right. Before I end, I want to mention that actually there are many, many ways of making quantum computer. It's not necessary just to be the quantum computer made by the others, all the 3 schemes. There can be more actually. So traditionally, every quantum computer made by this circuit-based design, just like what our classical computer right now or cell phone is, right? You use a qubit, use a bit, or use multi-qubit gates for that. But actually, a quantum network is also can be a quantum computer. So people think about if you make a big quantum network, you can actually use this Merriam-based quantum computing to make it a one-time quantum computer. So therefore, there are many, many possibilities to make a quantum computer. Let's see how things goes in the research now. So this is all I want to say. Thank you for your attention, and I'm happy to answer any questions.
谢谢杨教授。这个问答的环节就我们留在最后了。现在下来，我们邀请就是国立先生讲一下从应用层面在那个量体计算是怎么样的。国立先生是 AWS 积分解决方案架构师国立先生请。
OK， 可以看得到我屏幕吗？
看得见，很好。
OK， 行，好 ，OK， 行，那我给大家稍微介绍一下从亚马逊角度的量子计算。OK， 那么说我来自亚马逊，是亚马逊中国资深解决方案架构师，在北京，然后。我的这个 topic 可能会20分钟时间，大概分3个部分。第一部分就是介绍一下量子计算，第二部分就是亚马逊，然后第3部分会有一个 live 的一个 coding。OK， 那么说这其实就是我们刚才杨教授讲到的这种量子计算了。那么说其实它相对来讲是一种全新的一种计算模式。然后 我们来看它主要针对于哪些问题啊？比如说从应用的角度，对于这种计算化学呀，对于这种材料科学以及一些跟图相关的一些优化理论，其实会相对用量子计算会比较多一点。OK，那么说我们来看什么是量子计算机。那么说其实就是用了这些这种微观物理世界的这些量子技术，来有一个比较好的一个全新的一种计算体系的这么一个这种超级计算机。那么说，这也就是我们刚才杨教授讲到的这个我们这种classical bit 和这种 qubit 之间的一个区别。那么说，我们来看这个区别，其实最大的影响对于计算机来讲，其实是对于内存的这么一个需求。如果说我们只有3个量子位的话，其实大家可以看到，它其实需要可以表达8个的这种数字。那么说，如果是像刚才提到的这种 Google 的这种量子的 processor， 那么说它实际上是可以几乎表达整个地球上所有的这些东西。那么说，所以说这其实对于量子计算机的设计造成了一些非常大的一些挑战。OK，那么说这是我们讲的一个量子计算的一个电路的一个设计。那么说左边是一个波尔的设计，右边就是我们提到的这种在量子计算领域里面的这样一个电路的一个设计。OK，那么说我们来看一下，在实验室环境中，大概从哪些维度来做这些量子计算的研究呢？就是说，比如说像我们提到的这些，然后这些其实都是完全跟物理相关的。那么说本身从我们计算的应用角度来讲，其实是期待着我们的物理学家能够把它给做出来，然后我们能够用。对 ，OK。那么说，我们来看从亚马逊角度，我们的量子计算的技术到底发展成什么样呢？那么说，实际上亚马逊在去年，也就是2019年和2020年初，发布了这么一个叫做 Bracket 一个服务。那么说，这个服务其实它是一个全托管的服务。那么说，这个服务其实是给科学家和开发者来研究量子计算。那么说，它主要是提供这么几个功能，第一个就是设计，然后提供了一个Jupyter 一个环境，然后接下来还有测试，然后还有就是实际可以在一个真实的一个量子计算的 hardware 上能够来跑这种咱们的程序。OK， 那么说我们来看，这是界面啊，这是一个我们的一个托管的一个 Jupyter 的 lab。那么说，我们可以在上面实际去写一些 Python 的程序，然后本身 AWS 会内置一些环境，能够有 SDK， 能够让大家直接在上面来做开发测试，然后相关的一些量子计算的一些算法。OK，我们来看，它就是怎么实现的呢？实际上，它是利用了我们叫做一个 serverless 的一个技术，就是说，实际上用户编程序其实是在一台亚马逊托管的一台服务器上，然后当你提交作业的时候，它会把它真实的提交到在亚马逊美国美东和美西托管的这么一些量子计算机上。然后由那上面来做执行，然后完了再把这个结果返还给最终的一个客户。所以说实际上可以相对来讲，就是说让每一个人能够使用得起这种可能在这种非常非常昂贵的这些量子计算的一个设备。那么说。这个图其实是我想show一下，就是说，这是我们真实的一个环境啊。然后左边就是用户，那么说他通过我们刚才谈到的一个 Jupyter 的一个lab 的这么一个环境，然后来做一个程序的开发，然后通过Amazon Bracket 这个服务，然后提交到我们后台的这种量子计算的 QPU 上，然后那么说。这些数据其实是放在Amazon 的 S3 的那个存储桶上，然后当然我们还配合有些那个CloudWatch 来做一些监控，所以说实际上这是整个就是从 Amazon 角度提供给科学家和开发者的这么一个量子计算的一个环境，所以说实际上大家可以看得出来。OK， 这个环境其实相对是比较友好的。那么说，所谓友好呢，就是说，它其实屏蔽了大量的量子计算的一些细节，然后它通过一个相对大家比较友好的一个Jupyter 的这么一个 Python 的一个编程界面，然后能够让各位能够比较能够非常落地的能够使用这个量子计算机。OK， 那么说，在底层的硬件上，Brocade 现在提供这么3种的这么量子计算机的技术，就是说实际 real 的一个产品，一个就是我们那个 D-Wave 公司的，那么说，这是它的一款量子计算机，然后中间呢是 IQ 的，然后右边的是那个 Rigetti 的。对，那么说实际上，这3家其实都是基于不同的，底层的微观物理的一个技术来做的一个量子计算的一个实现。那么说 Amazon Bracket 其实就会在它上面封装一些接口，然后通过这些接口，然后供全世界所有使用 AWS 的这些用户能够通过 API 的方式使用这些机器。那么说实际上。待会儿我们会有一个 live code 的环节，就会给大家展示，就是说你可以声明一个设备是 D-Wave 的，还是 IQ 的，还是 Rigetti 的。对，那么相关的会有一些开发的 SDK。那么说，所以说其实大家可以看到，就是说在从 Amazon 角度这么工程化的一个领域，实际上我们是把这个量子计算机本身，交给了像杨教授这样的科学家来由他们来去做，然后呢，而实际上从工程角度，我们是把它封装起来，通过一个这种我们讲的叫托管的一个环境，然后通过 SDK 的方式，然后供开发人员来直接使用这些不同技术的这种quantum computer。OK，那么说本身 Amazon 还会有一个 quantum 的一个 solution lab，那么说用于这种跟这种开发者合作啊，包括一些跟学校的一些相关的一些合作，然后共同开发一些有针对性的一些 solution。OK， 那么说接下来我会进入一个 live coding 的一个环节，所以说我会稍微推一下幻灯片。OK， 那么说大家可以看一下，这其实是一个 Amazon Bracket 的一个服务。那么说我们登录进来，大家可以看得到，这是我们一个 console。那么说在这 console 中，各位可以看到，其实有我刚才提到的一个 D-Wave。那么说有2个机型，一个是 Advanced System 1.1，还有一个2000。然后这边是我们的 IQ 的一个机器。那么说，最下面其实是Rigetti 的。那么说大家可以看到，就是这是它的量子位，对吧？然后这是它的系统状态，然后这是它是否可用。然后比如说像这台 Rigetti 的这些机器，其实大家可以看到，它现在在被其他的用户所使用，所以说实际上它暂时是不可用的。对，然后那么说，我们随便点一个进去吧，比如说我们点一个 IQ 进去。可能稍微，然后大家可以看到，那么说，它是在那个美东，在马里兰，然后这是我们计算的一个每任务的一个钱，对，一个收费。那么说，这是它的一个拓扑，对 ，OK， 这是我们讲的一个 OnQ 的 ，OK。那么我们再回来看一下那个Rigetti， 对，然后对，这是它的一个拓扑，对，所以说我们可以看到，等于是有这么多相关的一些计算资源，然后来给它使用。然后我们可以看到这边会有一个 device 的 ARN，那么说这是 Amazon 内部的一个标识，也就是说待会儿我们会在 code 中看到，当你想使用这台量子计算机的话，你要声明的使用这么通过这种 ARN 的方式来去显示的声明它。对，然后我们可以看一下这个D-Wave 的 ，OK， 那么说大家可以看到这是它的一些相关的信息 ，OK， 那这是我们回到这个device 这个界面。好，那么说，我在这边要补充一点的是，随着我们科学家会做出不断的基于新的这种量子技术的这些量子计算机，那么说 Amazon 也会不断的把它集成到这么一个系统中来，给大家提供更多的这种我们讲叫 QPU， 对吧？就是说一个 quantum 的一个 processing unit。OK， 那么说我们来看这个 notebook 其实就是我所讲到的，就是我们其实是一个托管的环境，它其实是一个 Jupyter notebook 一个环境。那么说用户通过这种方式就可以来做一些相关的基于下面 QPU 的一些 coding。 OK，那么说来看，这是我们的一些代码。今天我给大家大概有这么几个代码要给大家稍微演示一下。然后我们来看这个，这是我们第一个电路，对，然后我们用 Bracket 的 Python SDK。OK，那么说这个程序其实就相当于 Hello World 一样。然后我们来看一下执行。然后我稍微给大家解释一下，这是一个 Python 的一个GUP 的环境。那么说每一个其实 cell 其实都表明它是否运行，然后我们可以顺序的来执行，然后这些 cell 其实是用于显示文本，那么说这些是 code， 好吧？那么说我们不断的去 run，OK，那么说我们在这步其实是引入了相关的一些编程的环境，比如说 Amazon 的 Bottle3，然后还有 Bracket 的这些包，然后大家可以看到就是我们这里面有 AWS device， 还有一些模拟器啊电路，然后那么说我们可以把这个 bell 的一个状态，大家可以打印出来。大家可以看到 Q0 和 Q1其实是吧，就有相关的一些信息。那么说 ，OK， 那么说我们再来看声明一个local 的一个模拟器，对，然后大家可以看一下。然后这个时候我们可以打一下它的 counter， 然后所以说实际上可以我们在00、11都有各自的这种count 的一个值。OK。然后我们现在各位可以看一下，这是我们得到相关的一个 account ID。那么说我们在一个托管的一个模拟器，也就是我们讲叫 SV1 上来去声明这么一个设备。大家可以看到 device， 然后 quantum simulator， 然后 SV1。OK， 那么说这就声明好了。然后接下来我们 run 在 QPU 上来 run 一个东西。好。那么说，大家可以看到，我现在声明了一个设备，是吧？就是刚才讲的那个Aspen One 的，就是这么一个东西，对，就是它，regetted。OK， 好，然后这个其实我们定一个任务，当然这个任务可能会跑得比较长一点，然后我们先让它跑着，如果是1天后的，我们就自动会把它超时，对。那么说 ，OK。那么说，现在我们其实相当于是跑了我们第一个这个一个 Python 的程序在量子计算机上，然后大家看到这是沙漏的一个图标。OK， 我们再看接下来的程序啊。那么说，这是一个退火算法的一个程序，我们其实是为了找到最小的一个这种覆盖。那么说，我们来看这样一个东西啊。我们大家稍微快一点，然后这是我们是用到了一个 DWave 2000Q 的这么一个 QPU， 然后我们是依然是大家可以看得到，就是说这是我们装载了一些相关的一些存储的桶，然后这个时候呢，我们定义它是5个 node 10个边，对 ，OK， 然后呢，好，我们来 run 一下这个结果。对，然后大家可以看到，它这边是星号，对吧？然后这个时候它其实在后台做相关的一些计算，然后我们可能需要稍微等一下，然后它会出一个结果，然后这个时候我们就能够解决这个最小这种边覆盖的这么一个问题。然后大家可以看到，这是我们0134，然后整个这个vector 的 cover 是4，然后我们稍微改一下这个程序啊，比如说我们把这个改成50个节点。对，然后我们可以重新 run 一下。对，然后大家可以看到这个星号表示它在运行，然后大家可以看到它会出一个新的结果。对，所以说这其实是表明我们在量子计算机上其实用了 DWave 的这么一个设备来做真实的一个编程。好，然后 OK。我们再来看一些亚马逊官方的一些例子啊，然后这是我们的官方的一个 sample， 然后这也是同样的，我们要在这边创建一个这种电路 ，OK， 然后这个时候我们就把相关的这种bit string 给打印出来，然后并且画一个图，对，所以说这其实刚才这个 demo 1是一样的 ，OK。然后接下来就是我们看的这个一个就说几赫兹的一个状态，然后我们来稍微看一下 ，OK。那么说这其实是一个相对比较复杂的一个物理问题，然后我们去 set up 这么一个电路，然后这是我们 大家可以看到这个电路其实是这个样子的，是吧？从 Q1 到 Q0 到 Q9，对 ，OK。然后这是我们本地的一个 simulator。好，那么说这是相关的一些实验数值。OK。好，我们可以稍微等一下它的这个运行。好，我们等它运行完，它会把这些东西都给打印出来。OK。好，我们在这个程序，大家可以看到，这个时候其实你看会有一些相关的结果输出，然后50个 qubit。OK， 那么说这是我们做另外一个事情。然后接下来我给大家看一个比较实际的一个案例，就是刚才我们讲的一个覆盖问题。对，那么说这是一个比较基础的一个 demo。好，我们稍微给大家解释一下，这是前面引入一些相关 D-Wave 的一些计算的包，然后包括一些 Python 画图的一些函数。好，我们接着往下运行啊。然后这个时候大家可以看到，我在这边其实是声明了一个设备，就是这个2000Q6，也就是说，其实是这么一台机器，对，就是这样一个东西。我看一下，稍等。对，OK， 没事，我们从这儿进一下就好了。好，那么说，我们接着往下运行。好，我们把前面这些初始化的程序都给跑完。好，我们来看，这是我们在六个点的情况下，然后我们画这么一个图，好吧？然后 OK， 我们回到刚才这个界面上。好，我们来看这个，就是刚才声明的是这么一个 QPU， 对吧？然后它现在是可用的，对，所以说我们接着继续。OK， 那么我们现在是在第11个 cell。好，我们来画这个图。对，大家可以看到，这个时候其实，我们找到了这个 MVC problem 的，然后我们这个是中心节点，对吧？然后这样的话，以这个维度来做最小的一个连接。然后我们来看稍微复杂一点，我们比如说把这个问题变复杂，变成10个点和20个边。对，然后大家可以看到，这个时候其实是一个相对比新的一个图，对吧？然后我们在D-Wave 这么一个 QPU 上来跑这样一个 problem， 然后我们实际上能够看到它是，就是我们找到了这个红色的这些，对吧？就是说1、2、3、4、5、6、7、8，对。然后这样的话，其实相当于是，等于我们实际是在一个 D-Wave 的这么一个 QPU 上来去求解这么一个 MVC 的一个 problem。OK。然后大家可以看到，这个时候我们尺度就会变得更大一点。我们在100个 node 和400个边上去，对吧？然后我们再来看去求解一下。然后这个时候要稍微等一下。OK， 然后在它运算的时候，我们稍微解释一下，就是说，实际上，量子计算在今天依然处于一个比较领先的一个前沿的一个阶段。大家可以看到，我们在这个100个 node、400个边的维度下 ，MVC 的 problem， 其实我们也会得到一个比较快速的一个求解。对，那么说，同样这个问题，如果是在传统的计算机上，可能会花费更多的一个时间。那么说，这也是我们在刚才幻灯片上讲到一些优化问题，其实我们是可以通过这种完全新的这种基于微观结构的这么量子计算机来去做更好的一个问题的一个求解。对 ，OK， 那么说这是今天的一个整个的一个 live coding 一个 demo。那么说稍后我给大家分享2篇 blog， 这是 Amazon 的一个 blog。那么说这是我们一篇就是关于 bracket 的一个 launch 的一个 blog。 那么说，然后这个就是一个 hands-on 的一个相当于一个小的一个 lab， 对，这是另外一篇 blog。OK， 然后这是我们整个 bracket 一些 document。那么说，我们基于所有的这些Python 的 API 啊，都可以直接在上面去点击，然后相当于是可以直接用这些东西来做相关的一些 coding， 对，然后这就是这个 live coding 的环节。OK， 然后我们接着回到幻灯片啊。那么说，这3个链接其实是刚才我 share 给大家的。那么说，分别是我的 blog 和这个相关的一些文档。对，然后那么说我稍微总结一下，实际上对于量子计算来讲，从工程的角度，还是抱有非常大的一个希望的，就是说，但是某种程度上可能需要3到5年或者更长的时间，我们才能够找到一些真实的一个商用的一个环境。那么说，所以说我们可以看到，就是说，尽管这个东西它非常非常的有前途，但是实际上，某种程度上，因为确实涉及一些微观物理学的东西，可能还相对，距它真正商业应用可能还存在一些价值。那么说，在这么一个阶段，那么说 AAMA 其实是提供了这么一些，相对比较友好的一个环境，能够给我们的这些研究者，给我们的一些开发者，能够在量子计算机上去做更好的一些相关的一些工作，对吧？不管是研究性的，还是一些真实商用的一些工作。那么说，这也是目前从 AAMA 角度对量子计算的这么一个一个态度或者一个方式。也就是说，我们在底层我们会集成所有能够集成的相对成熟的这些真实的 QPU， 然后在上层我们通过 API 的方式，然后给算法科学家以及相关的这些工程人员暴露一个比较好的一个开发的接口。同时，正是通过这种方式，我们才能够让几乎每一个人，不管是这种 PhD 也罢，还是一些学生也罢，让他真实的能够用得到这种量子计算。所以说，这也是从 AWS 角度一个非常重要的一个意义。好，那么说最后一页就是说，如果各位对那个AAMA 或者说相关的这些技术感兴趣的话，大家可以直接发邮件或者去订阅相关的这些 email。然后，好吧，那么说我的这个 session 就在这边。好 ，Eric。
谢谢郭先生。
OK，
接下来我邀请李明阳先生从投机的角度去看一下这个量子计算的这个科学。
Hello。
李明阳先生是香港科议员，投机基金分析师。李先生，你可以开始了。
Okay, I'll share my screen here. So give me some time. Wait.
Okay, I can see it.
Okay, can you see it? It's all right?
Yeah.
Cool. Okay, well, thank you AAMA for and HKS TV Ventures to co-organize this event, and also CIDE. So I'm Kenneth, and I'm from HKS TV Ventures. So as you can see, this is the science park here in Hong Kong, and we are the corporate venture fund to invest in deep tech companies. And today I will share a bit of my view on quantum computing, as it's a lot. Well, we're currently looking at a lot of different spaces in technology, and quantum computing as a very hot topic recently is definitely one of them. So I'll just share my views on that. But what exactly is quantum computing is that, as Professor Yang has said, it's not a replacement of classical computers. It's people hypothesized that, like Richard Feynman hypothesized it at around the 70s, and it's used to solve some very hard problems that traditional computers can't solve. So you can see here, this is called the traveling salesman problem, is that when you have say, imagine you have 6 or 7 points here, cities, and the traveling salesman has to decide which one is the shortest path to go. And then for the computer, they just do it brute force and then keep trying until they found the optimum distance. But what you can see here is when you have more nodes here, that the computational complexity gets harder, gets way harder as it goes by. So normal computers right now can't solve this, but people in the quantum computers are finding some algorithms that can solve it in a reasonable time, which is not 2,000 years here, but maybe within a day or so. So it's a very interesting space that people have been looking at. But why don't we share some news here? So this week, or actually last week, well, a few days ago, is that there is a UK-based quantum computing company called CQC, which does a software enterprise solution. They announced a partnership with Aker BP, which is a Norway oil company, basically. So this is called, they have a partnership in something so-called the quantum machine learning. So it's so in oil industry, from my understanding, is that there is something called multi-phase flow, which is when you have this oil well, when they produce something, it's usually a mixture of gas and liquid. So when we say phases, we refer to solid, liquid, gas, and there's a mixture of those, and they have to deal with this some chaotic fluid dynamics here. And so somehow CQC runs their algorithm with their platform T-Kit here in the IBM's processor, and they found that they claim that they have some pretty good results compared to the classical machine learning algorithm, and Aker is really willing to try out more with CQC. So they announced a partnership, and this is very interesting. It's probably one of the earliest application of a quantum-driven machine learning or AI in the energy sector, or in general in this industry, to try to demonstrate some commercial application. But we're still here to see if this is going to be something great. But when we look back in 2020, so there are around 0.9 billion, around 1 billion of private capital flowing into quantum technology companies and 34 funding events. So that's a pretty good compared to previous years. So it's not big compared to, say, AI or other technology, which has already demonstrated some promising tractions. But I think the market is quite optimistic to the development of quantum computing, especially in the startup space. But a few of the big news here is, of course, SC mentioned that there is a quantum supremacy claim in China. So when we say quantum supremacy, what we mean is that there are things that classical computer simply can't do, but they have made quantum machines that calculated something that is in a way, in a fashion that's way faster than the computer right now. So yes, and the USD in China in Hefei, that they claim the quantum supremacy using its photonic quantum system in Zhejiang, and then that actually sparked a lot of debates, just like the Google and IBM debate a few years ago. But I think it's an interesting space. So interesting debate to see that the professionals in the space is actually getting really engaged into making things rigorous. So one of the things is about programmability. So when you have this computer, you want it to be programmable and do a lot of things, not just one single problem. So, and they have to really dig down on how programmable different computer is. But I think that's a next question in the academic space. And also there's a quantum IPO, actually, not exactly in quantum computing, but it's in quantum information security called Quantum CTech. They got listed in Shanghai, and the shares actually got really high at some point. They does quantum communication, which China is actually taking a pretty strong lead in this space. This is slightly different from what we're going to talk about in quantum computing, but it's also something pretty interesting to see in this space. And also for funding events like private capital, like venture capitals, like the work I'm doing, are actually pouring money into various promising startups. As I say, CQC got their Series C, Zapata at Harvard got their Series B, and so on. And also IonQ got their announcing their next generation ion trap quantum computer. So they're pretty, despite the pandemic, there is actually a lot of good news in this space. So I think the market is going to see a lot of more of these things in the future. But let's take a step back and assess what we are at right now. We're in an era called the NISQ as as Guoli has mentioned, which is the noisy intermediate scale quantum, which means that now when Professor Yang mentioned that the quantum bits are very fragile and they're very susceptible to noises, what we are seeing here is people manage to build something. They can't get rid of the noise, but somehow they work in a slightly noisy environment and may perform some sort of task that can demonstrate quantum advantage. So this term is coined by Professor John Preskill at Caltech. So we are seeing something, some sort of functional quantum computers here, and in this within these few years, we are seeing that the focus in the space will be in how to mitigate the errors. And with this limited capability, certainly it can't do things a trillion times faster in a commercial aspect, but they can still do something. One of the things that people are seeing a promise is in quantum simulations, is to simulate the materials, which are inherently have a lot of molecular dynamics, and you can replace the wet lab testing with quantum simulations in a computer. So people are actually trying these out, and we have, I think we are at least 10 to 20 years to see the actual quantum computer that people in academia are actually thinking about, the sort of noise-free, clean ones. But we can certainly be hopeful to that. So I highlighted here, this is where we are at right now. I took a lot of insights from some of the good reports from some management consultancies, say McKinsey and BCG, so I also cited them here. But I think it's a good thing for the audience to take a look at them. They're extremely good articles. So in this era, what are the machines available? Like when Guoli mentioned, there are a few machines that the AWS is supporting. So there are two types. I think it's really in a leading position. One of them is a superconducting circuit. Another one is trapped ion. And as you can see, the superconducting circuits and qubits are mainly made by Google, IBM, these kind of tech giants in the space. So the reason why is that they built on the existing semiconductor and CMOS technology that they have a very strong access to in the Silicon Valley, and it's easier for them to develop. While these ones here, the trapped ion, are mainly from university spin-offs, which they have a better command in the laser technology to manipulate the ions. And they have all their pros and cons, and they're really competing technology right now. And in here, if you know something about superconductivity, you have to cool them to a very low temperature, and also the qubit is rather more fragile than the ion ones. But at the same time, the trapped ion quantum computers have problems with scalability and speed. So there are many experiments that people are running in these two leading technology, that if you actually take a closer look to the startups and the space, which I'll also introduce later, you see these two are the other major ones. And also there are topological quantum computing, which is done by Microsoft, but that's a slightly more far-fetched but promising theoretically, which I wouldn't mention here, but I think if you're more theoretically minded, I think you should take a look at that. So how about the algorithms? How do we teach the computer to do things? It's in NISQ, the algorithms are also important. When Professor Yang mentioned this thing called Shor's algorithm to crack the RSA encryption, which is based on prime number factorization. Are we seeing that in the near future? Not exactly, because when Peter Shor and other theoretical physicists or computer scientists draft out these algorithms in pen and paper, what they're assuming is a noiseless environment. And this is what I'll classify algorithms in two segments. It's called the purebreds. So it's theoretically proven that they're extremely fast in solving some problems, say Shor's algorithm. But the point is that in a physical system, they have to require a long sequence of flawless execution, which is pretty much impossible in nowadays. And and certainly we don't have to worry that we have quantum computers to break the encryption, say our talk here, in the near future. So I don't think we should worry too much about it. but also there are another type of algorithms that people have developed, like the ones maybe in the CQC and Acre deal, is that some sturdier algorithms, but which is slightly more resistant to errors. But then, so they can be run in the machines right now. But the point is, are they faster? We don't know. So in the next few years, there are people doing a lot of experiments, and this would be really interesting, I see in here. So this is the highlight of the NISQ era. So why do we need quantum computing? So we have a lot of applications in this space, of course, and this is just to name a few that people are trying to guess. And I think from the industry's perspective, we really have to prioritize which ones are coming and which ones will come slightly later. So I highlighted these few ones, and I think the industry are tending to think that the machine learning and the quantum chemistry simulations will be the leading applications given the technology we have, and for pharmaceuticals and cybersecurity, these kind of applications will come slightly later than that, when the fault tolerance are getting better. When we say fault tolerance, it's about the quantum error correction that we really have to have in running these systems in a proper way, and this is very hard. So which I'll talk about later. So I highlighted this as well because this is predicted a few years ago, and this literally happened like last week. So I highlighted this in the energy sector, which quite interesting. And I think we can simply think of this as, when we do R&D, they have a lot of wet lab research and a lot of chemistries are involved. And so you can replace those experiments with quantum computing, or in general, high performance computing, to take over those long and tedious work that is based on trial and error and inefficient. And you can see a lot of large corporations are leading efforts here. Goldman Sachs in derivative pricing. There are a lot of joint projects. These news are pretty recent, and there are even more news in the past few years. And this is really seeing that the industry, what they think is to get their quantum literacy, so to lead the effort to understand what this technology currently have and will have in the future. And when they get mature, these companies could be the one that has the first taste of their advantage. And really, we are in the budding stage, or what we call the vacuum tube stage of quantum computer, like when they back in the 60s, where the computers now are in vacuum tubes. This is where we are at right now, that we're trying to get it to work and do good stuff. So so yeah, when I say the near-term market opportunities, say what the technology will and what we're seeing that will have a pretty good result is, one of them is in quantum chemistry, which they can lower the cost of experimentation, I'd say. So in a lot of things like fertilizers, materials, drugs, energy systems, just a lot of things that can be done in a chemistry style. This can be rigorously tested in the quantum computers. As I say, you're simulating quantum system with quantum systems, and that's they're naturally what these computers and machines are good at. And also we are seeing some tractions in quantum machine learning and AI, which is a mixture at this point, would be a mixture of classical and quantum algorithms. Some of the audience here might be more familiar in the AI space, so I don't mean to. I certainly am not. I'm just trying to make a rough guess of what people are really seeing here. And when they're testing out this machine learning, as I say, people are really experimenting on, are these quantum machines faster, and how faster will they be in tackling these more complicated problems? And these things can happen without the machine, this kind of research, especially, and a lot of companies like CQC, Zapata, and a lot of software enterprise solution companies are working on that. This is easier to develop in terms of they are not very capital intensive at this point. So really, the software is developing way faster than the hardware nowadays. and we can see how they can address of the problems. And also in finance, that some of the more quantitative firms in hedge funds, which require heavy computation analysis in Monte Carlo sampling here, might find some angle in adopting these kind of technologies in devising their investment trading strategies and stuff, especially in the very volatile markets. And so this is the ecosystem. So what we see is that when things get more serious, there will be more different people doing different stuff naturally, and we are seeing the trend where different companies are focusing in different things, where they have this map here. So we see the end-to-end provider is the full stack providers, where they do the entire thing from hardware to software to services. Of course, these ones are often affordable only by large corporations like Google, IBM, and also Amazon just now, as Mr. Guoli has said, is entering the space as well, having their own Amazon Bracket service. And also these one other, you can see these ones right there are more in the startups. IonQ is one of the leading trapped ion quantum hardware company, OQC at Oxford, IQM at Finland. These people are making strong hardwares, and the way they appear is they usually are university spin-offs, which the frontier research happens in institutions, and when they see a business opportunity, they spin off, build their own company, and sell their stuff and get into the business space. These ones are also in the these ones are in the software space. Riverlane makes the OS, CQC Zapata makes the algorithm and the enterprise solution that actually to translate the problems of real world problems into a way that can be done in quantum computing, and also have different more specialized people in various spaces. Q Control, I'll have a few case studies later on, and Q Control is here. And well, Amazon, I dedicated a page for it, but I think Mr. Guoli has spoke way more than that. But they announced this bracket last year, having these machines, and also a few days ago they announced setting up a quantum computing lab in India, Amazon and the India Ministry of Electronics and IT. But really, when we think about in the business side, we have to think about how they're sold. So when we talk about investment, we see how the company's founding profile and what kind of investors they have. So I took these two cases. This one actually has got some Hong Kong funding because Horizons has funded them. OQC is from Oxford spin-off, which I'm slightly more familiar. And you can see this one does the control system cloud platform. What they do is they do a software subscription model. And for one, so when you don't expect quantum computer to be sold machine by machine. So how they're going to do is, although a lot of changes have been made soon, but it's called the QCAS, quantum computing as a service. So it's sort of like a cloud computing where you send where you can access their computing system online, and they do the computation for you. But many things are really changing. But these are the emerging ways of doing the business in this space. And also this is a segmentation of fundings, but this is pretty outdated. But you can see US taking a big pie here, and full stack and computer hardware is taking the majority. But I think this is going to change soon. Actually, there will be more investment in the enterprise, as you see later in 2020. This one is in mid 2020. In the later 2020, there are more fundings actually in the software side, which has been previously neglected. And other quantum technologies, which I have not been mentioned, but they're pretty hot as well. I think I'll actually dedicate a few words here because China is leading a strong effort in this space. Is basically a hack-proof way of communication based on quantum mechanics. It's a physical way of protecting your communication rather than a cryptographic or mathematical protection. And so China, I think has a leading effort, but I'm no expert in that. And also there are, when we see quantum computing crack codes of crack very hard codes here, we can see that people are developing new ways of protecting their information from quantum computing. So these are the things that people are looking at really. But what do we see in 2021? I make a few wild guesses. Could be right, could be wrong. You don't have to take my words, but you see I think there'll be more quantum advantage supremacy claims by different companies, which have been happening again and again. And also there will be as the industry getting more interested in here, there'll be more talents migrating actually from the academia to industry. One of the physicists that I really respected is actually migrated from Oxford University to actually doing the chief scientist at CQC, Bob Koech, one of the leading quantum logicians in this space. That this is really demonstrating how attractive this space is, and also more fundings, I'd say, that people are getting more access to what quantum computing is doing, like the talk we're having now, and also a stronger race between these two platforms. But I think there will be more government funding, as we do feel that there is more government attention to this technology, and they really want to get in hand in national level. But there's one last point that I'd like to make is, although there are a lot of optimism in this space, I really hope that people wouldn't get too optimistic in this space, because I think it's still going to take some time to see actual commercial applications. And if you're too optimistic in here, and when the startups or companies actually fail to deal with the over optimism, the industry perspective, according to different analysts or associates, will be slightly dimmer. And I think it's quite detrimental, and it's good to be not to be overhyped. And at last, what we do here is, as a venture capital arm of HKSDP, we do actively invest in innovative entrepreneurs in the deep tech industry, and we have a mission to cultivate this innovation ecosystem in Hong Kong. And by providing our endorsement as a science park, we leverage a lot of private capitals and leading institutional investors to invest from the society benefiting technologies from cancer genomics, autonomous driving, and new materials. And I hope this talk will answer a lot of your questions in the quantum computing space. And thank you again for having me here.
Thank you, Kenneth. Thank you. 这里我们有一些问题要我们的听众在问的。第一个问题就是说 time travel. Can we use the quantum computing to simulate time travel? 杨教授，你可以讲一下吗？
Well, I think the quick answer is not really likely. So I don't think this is really right now people are really dealing with this. I don't think so. Of course, people are also saying that right now, since people can do this so-called quantum teleportation, and then people make another connection there. Say, for example, you can teleport human being far away, but I would say this is more in the scientific fiction direction, but not really practical in reasonable time scale, I would say. So I think we can just treat it as yeah, exactly. So people right now dealing with a very small scale, very simple things. For example, even the quantum teleportation, people can just deal with some photons, right? So we don't go very big in the degree of freedom. So let's not even mention about human being, right? It's not really meaningful for many, for microscopic scale stuff. So that's my feeling.
谢谢，明白。其实第二个问题就是收费的。国立，你可以解说一下吗？我看见你有些解说。
OK。我在群中回了。There for simulator, Armageddon Brockie SV1 is built at rate 0.0 0.075 per minute. But for the real QPU in the AWS, we have two pricing model. One model is per task by price, and the price is 0.3. And the other one is by per shot price, and the baseline is 0.00019 per minute per shot. OK。
好，谢谢。还有一个问题我问的就是，现在我们有很多 startup， 他们希望在这个 quantum computing 做一些东西。Kenny 有什么建议给他们作为一个 startup？
Hi. So did you say or startup wanting to go to the quantum computing space, right?
Yeah. What can you do as a startup? Yeah.
What I see here is that a lot of startups in this space there are a lot of university spin-off that the founders are really technically minded, also all kinds of PhD in the relevant spaces. This is the majority of the things that we see here, and if they actually really go into the bottom of the foundation of the hardware, which people are putting a lot of effort, and if one startup actually get into this space and become the winning architecture, they will be the winner, and they takes a lot of credit and advantage in the business sense. But other than that, if a startup want to get into this space, it definitely has to be technically minded. But I think one of the things that in the startup space that many people might not have give too many thoughts on that is actually how to do the business. So when you build a machine, how this thing can be translated into business value and make money, or in a way that can be delivered to people or enterprises. From a venture capital perspective, we've seen like very brilliant scientists and academics. They have a really strong research, but I think it's the effort dedicated to how to commercialize them is slightly less. I think it might be too early to speak on that. But when I just now presented 2 case studies where I told people about how these things are sold. I think this is really up to a lot of different discussion that in a startup they have to think you're not a research institution, you're a company, and really you have to think about how to sell them once you have this machine.
Other than building the quantum computing, I think what about on the application area? I mean, can the startup make use of quantum computing to build application? I mean, particularly in the Greater Bay Area, the GBA area. 在大湾区，他们可以利用这个 quantum computing 去建立一些应用嘛？还是这太早了吗？现在是
That's too early, I think.
Too early.
Too early. I think it is still hard to say to be more specific to a geographical area. I think this is a very global effort right now in the quantum computing space. That's why a lot of startups and big corporations are partnering with each other. But as I say, the immediate applications will be in the quantum chemistry side, where material simulations, and I think one trend is that some startups are more focused in specific applications of quantum computer, which might answer one of the questions. There's a question in the Q&A floor. Mm. Some startups are more focused in saying they do specialist applications like pharma R&D. So they put more effort into say how to use quantum computer to do simulations for pharmaceuticals or chemistry. I think this might be one of the direction that has been getting less attention, because people are still putting a lot of attention in the hardware side at this point, or actually not many people are putting attention in the quantum space because it's not easy to access, I'd say.
Thank you. 这个从这个 AWS 的层面，你在提供了这个 quantum computing 给一般的用户，这个用意在什么？现在是不是太早了？ 哎，郭先生。
对，其实好多客户，只是用来try 一下，并没有实际的很多 commercial application 在上面跑。对，确实有些早。
但是也是一个很好的学习机会嘛。好，谢谢大家。看接下来我们的问题也差不多了，都回答。有一些剩问题。有一个问题就是 ，What do you think the key technical challenge is building the quantum computing？刚才这个杨教授也说了嘛，杨教授你可以再讲一下吗 ？The technical challenges.
I think this technical challenge is quite hard, both in the fundamental science and in engineering. So because right now, look what did people made so far, right? So we didn't even make one logic qubit. So think about what the counterpart of a classical computer did. So you can think we go very early age, actually. We probably go in the early 1940s, 50s situation. Where at that time, people already make one logic bit in the classical computing, but here in quantum is not yet there. So it's still quite, people may completely overthrow current design, current architecture, current physical system, because this fundamental problem may not be solved easily, right? So don't be surprised after 5 years, people say superconductor Johnson junction have no future, or trapped ion will not work. This is very possible to happen because look, people is coming to the bottleneck. If you take a close monitor of what Google did recently, right? So after 2019, they post this quantum supremacy with 53 qubit. It's already more than 1.5 years now. So there is nothing. So we don't even have this Moore's law, right? So Moore's law said, every 2 years you double the actually they double the logic bit, right? So that's even more demanding than right now. We don't even have a logic qubit. But let's lower down standard. We double the physical qubit. It's still hard. People don't make many breakthrough. So it's very likely that we have to try another way to do it. For example, a new system, a new way of making quantum computer. So this is more to the fundamental science point of view, because the error could be very severe. So this is also answer to other questions. For example, they ask now the application, for example, can we simulate the design of COVID-19 vaccine? It's very hard. So we think quantum computing eventually can do this quantum simulation, but look right now what we have. We have qubit that loses quantumness within a very short period of time. So we cannot use it to simulate a meaningful material. We cannot even crack the a password. So think about this. We want to crack this RSA code. So we can compare with just my laptop right now in front of me. This is a classical computer with very, very simple design and very, very cheap. So with this computer, I can crack like 100-digit prime number within an hour. This is everyone can do it. You can just download this program to crack the 100-digit number easily within an hour. But think about how is right now all the quantum computers do. So if you ask them, say, I blindly give you a number, you factorize it, no one can do anything. So what all the demonstrators now doing is, for example, they already know you give them a 15 or you give them 21, you give them some number, and they use classical computer first to help them to come to a certain stage, and then they put in the quantum computer. It's not so not even a fully running of shell algorithm yet, because even the shell algorithm for a very simple situation, you need a lot of qubit. So this is something right now none of this computer can do. So that's why the demonstration so far eventually come to us, for example, simulate a random quantum circuit as output, right? So they cannot run, for example, a demonstration of quantum error correction, or they cannot run a blind running of shell algorithm. So this is the distance from the principle, the proposal to the reality. The reality is still quite far away. So that's So this is I mean, so people can ask question, right? So just do a real test, because now all are proof of principle. So we know that how far away from a proof of principle to a real practice in the industry. That's a many generational way, actually, usually. So this is, I want to say the comment. So I would not be surprised that after 5 or 10 years, people say, you know, we come to a complete wrong route, that we have to go over again to another way to demonstrate quantum computing. So I believe the quantum computing principle, all this algorithm, those idea for making simulation are really very important. But the way we reach it from the physics point of view or from the engineer point of view, we may come to the wrong path. This is possible. So we really have to explore with all the possibility, and hopefully there new mindset comes in that point to the right direction. So this is my feeling.
Thank you, Professor Yang. 有一个问题，我们在听你的问题，一个问题就是这个 cracking，crypto cracking 我看国内有一个答案是吗？有一个 demo 是，你可以说一下吗？1分钟。
OK， 关于这个cracker demo 实际上是没有的，我刚才找了一下，然后稍后我再发些邮件问一下吧，因为这种 cracker RSA 的算法好像是没有这个 demo 的。
好，有这个问题了。另外还有一个问题就是investment 的，就是 about the investment from China。So can 有什么补充吗
？Hi. Yes, so it's quantum computing in China. So yes, from I think it's referring to Vincent, the pie chart problem, right?
Yes.
Okay. Yes. I think the problem is that when it is referring to, I think the project is referring to VC fundings instead of government fundings. So I think what my views on the quantum tech in China is that they have a more strategic focus in quantum communication, which I think is taking a stronger lead in the global space. While for quantum computing, it's mostly in the institutional space. There haven't been startups nor the VCs in the China have a very strong interest in going into these spaces at this point. But if you say the investment trend, I think will be more in the quantum communication side, no matter from the government or the private point of view. As you can see, the quantum CTEX IPO last year has a soaring share price here, and this is seeing how I think China's point of view on that. But in terms of quantum computing, I think the UK or US especially have a stronger startup ecosystem in the electronic sector. I think they're still having a stronger lead, especially with the academic network. And also the infrastructure is slightly different, as the one in Zhejiang are actually using photonic quantum computers, which is a slightly less common ones in the commercial world. But I think my point of view is that people should pay attention in quantum communication more than quantum computing here.
Thank you so much. 我们还有个问题就是那个 freshman 问的，就是刚毕业的他想知道多一点 quantum computing 的东西，在什么地方看？我建议他留意我们 AAMA 的网站 ，AAMA 的一个资讯吧。我们会把今天的资讯都发在我们网站上，他留意我们的网站就可以了。好，谢谢各位，我们时间也差不多。好，最后我们主席毛遂哲先生颁发我们的感谢状。好，
谢谢。
毛先生有什么可以讲吗？
非常感谢3位专家跟我们分享这个我是似懂非懂了，对我来讲是非常前沿的东西。I don't even pretend to know understand these stuff, but look like it is real. I mean, we're getting application 开始有应用了，感觉是3-5年之后商业落地，可能3-5年之后就会商业落地了。而现在已经就所谓量子计算已经有一个生态圈，已经形成一个生态圈。除了科技巨头以外，还有初创企业的参与，看很多科技家创业， 杨教授，你什么时候创业？你一是知道怎么找投资者了？你这个地方没多远。二是也请通知我们，可能我们一些会员也有兴趣跟投。首先我们是给一个感谢，一个 certificate appreciation 给杨教授，谢谢杨教授。
多谢多谢
谢谢谢谢。
谢谢。
然后我们国立先生也感谢您介绍那个 Amazon 现在已经为那个所有量子计算提供服务了，你们还是走得比较前。一个也希望我们以后多交流。好，感谢国立先生 certificate appreciation。我们 Kenneth 科学员，香港科学员那个创投基金 Kenneth 给我们讲得很精彩，那个初创企业投资或者有些引进投资者关注这个领域了。Actually very good, Kenneth. Thank you, Kenneth.
Thank you, everyone. Thanks for having me here.
好，我们今天我们这场的科技沙龙都此结束，感谢大家。
谢谢大家。
好的，
谢谢，
拜拜，
再见，拜拜，
拜拜，
拜拜。
拜拜。